Jacob Bean on observations of exoplanetary atmospheres. Jacob is a professor at the University of Chicago and one of the world's experts both in observing atmospheres from the ground and from space. And he is the PI of still the largest exoplanet atmosphere Hubble program over the past several years. Jacob, take it away.
Well, good that I'm the PI of something that's the biggest, even with all those qualifiers. Good. Can you hear me? How's this? Excellent. Good morning, everybody. Sorry I haven't been here the earlier part of the week. I had some other stuff I had to do. I'll be here the rest of this week lecturing. I'm sorry, you have 4.5 hours of me coming up over the next 2 days, and then the next 2 weeks after that. Since I didn't get to talk about a possible project with me over this time, and also since I won't be here, I thought what I could just offer would be as a sounding board about observations of exoplanets. I think this workshop is mainly focused on theory, but if you have questions about observations, or you're thinking about an observational project, or you're thinking about interpreting some observations, I'm happy to talk to you at any time over the next 2.5 weeks about my perspective on that. As Jonathan said, I've been asked to talk about and review observations of exoplanet atmospheres, and that's a pretty big topic to cover in just 4.5 hours. Here's the outline of the way that I've thought to break this down. I'll start today with an introductory and overview lecture, observational techniques, a little bit of context, and motivation. The real meat of what I'm planning to talk about will start tomorrow morning with lecture number 2, where I have a substantial number of state-of-the-art science results that I'd like to go through. We may not get through all of those, but at least I think the slides will be posted online, and so you may find them as a useful reference, even if we don't get to talk about everything. And then finally, before lunch tomorrow morning, I'll discuss the future in terms of what I think are the open questions, some of the open questions in the field observationally, future facilities, telescopes, and instruments that are being developed, and then we may expect to come online on timescales ranging from just a few years to even decade timescales. Okay, so today, introduction and overview. I can't give any talk without beginning with the motivation and context, and so I have to do that, even though I think Jonathan gave a great introductory talk on Monday. I'll give an observer's perspective on why atmospheres, a very quick one, but my own personal perspective on that. I also want to talk a little bit about the solar system context. Solar system planets give us our framework for comparative planetology, and so that's the framework we're trying to export to study exoplanets, and so I want to say just a few words about that. And then the main part of the lecture today is going to be fundamentals of the transit and direct imaging spectroscopy techniques. And this will be aimed at a pretty basic level, but I think that's a good way to start just to get everybody on the same page. I think we have a diverse audience, and so I'll go over that stuff, and forgive me if you already know that. Okay, why exoplanet atmospheres? So here's just a chart that sort of summarizes the state of play discovery of exoplanets as of fairly recently, just a few days ago, where I'm plotting mass versus orbital separation, log, Jupiter masses, and AU for all the planets that are called known exoplanets from exoplanets.org. And I'm plotting here detections made with a number of different techniques and planets that we don't necessarily even have any mass information about. For example, a large number of these red objects are Kepler planets, especially in the bottom left-hand corner, that we don't have masses for. What we have are radii, and the masses are estimated. But just to pull all this together and put them all on a single plot, this is one thing that you could do that relates the most fundamental characteristic of a planet, its mass, to its separation from its host star, that says something about where it has formed and evolved and the amount of radiation that it's receiving. The point I want to make with this plot is we have a diversity of planetary systems around other stars, and that's the extraordinary thing that's been realized from the detection of exoplanets over the last 20 years. And there's parts of this parameter space that are yet to be explored, just from our observational limitations. But to understand the diversity of planets that have been revealed, I think exoplanet atmospheres, the study of the atmospheres, is the real key next step to understanding this diversity through comparative planetology. Another thing that we can take from this is that these thousands of planets that are known around other stars gives us an opportunity to further our understanding of planetary atmospheric physics and chemistry and planetary origins. This is, yeah? I think some of these gaps, for example, this one is a very prominent one. This is another prominent one. I think those are real. Yeah. So we're seeing real populations emerge. There's a continuum of objects, but there are gaps where you have objects that are less common in terms of separation from their host stars, in terms of sizes. This gap seems to be real. So these are real populations, and I guess what I'm trying to say is to understand those populations that are being resolved out of the larger group of exoplanets is studying the atmospheres through comparative planetology.
So just to make sure, the clump of hot Jupiters, is it actually a population distinct from the rest of the planets? If you look at the Kepler field, then there is no...
Yeah, I don't think Kepler is the best way to understand the frequency of hot Jupiters because since the frequency is so low, and I think the metallicity of the Kepler field is also subsolar, there's so few of those objects that statistics aren't great. I think where you're getting the better information is from the radial velocity surveys, which hot Jupiters are easier to find with radial velocities, but giant planets at 100 days are also quite easy to find. And so I think from that you realize this hot Jupiter population is a distinct population. There is a trough, there is a fall off in frequency of objects from say 10 days out to 100 days where it starts to rise again.
Okay, but when you say the close-in planets, when you say, the idea is that there's hot Jupiters, almost nothing, maybe like one Neptune, very few one Neptune, and there's like that gap at very close.
That one's also real. Yeah, so I was talking about this gap. That one is also real as well. Yeah, and from there, I think the Kepler statistics are what's really driving that information. Anyway, I don't want to get bogged down in this because this is really just setting a context and motivation for why we want to study the atmospheres. Now that we're starting to see these populations emerge, now that we have these numbers of planets, we understand them more deeply through comparative planetology, and we leverage the existence of these objects to further our understanding of these fundamental questions. And so I kind of frame these questions for atmospheres, what are they like, where do they come from? And so what are they like? That is, understanding how their thermal structures, energy budgets, and dynamics come about from the irradiation of our host stars, from the loss of the energy of the heat of formation, and doing that to understand planetary physics and new regimes, and also measuring compositions, molecular and atomic species, tracing that back to the underlying elemental abundances and elemental abundance ratios, to understand planet formation and evolution, because the atmospheres are a fossil record of the formation and evolution of the planets. And even though I'm talking about these questions separately, I think it's very obvious that you have to study both of these together to get a handle on either one of them, because, for example, if you measure molecular abundance, you can't understand what the underlying elemental abundance is without knowing the temperature. And the same thing is true for the thermal structure. You can't appreciate why the thermal structure comes about without knowing the composition of the atmosphere. So connected questions motivate holistic studies. As I said earlier, our study of the solar system planets gives us this framework for comparative planetology. And so I want to say just a few words about the solar system planets so that we're all on the same page. And I'm going to focus actually on Jupiter, Saturn, Uranus, and Neptune, because these are the planets that are the closest analogs to the exoplanets that we're actually studying the atmospheres of today. Of course, Jupiter and Saturn have their really stunning visual appearances, bands and zones. Their reflectance spectra are dominated by cloud species. They have internal heat and different rotation that gives rise to different phenomena in terms of these bands and zones. The source of the colors is likely some high-order complex molecules formed via photochemistry that we don't necessarily know the origins of. And so this gives us, even for giant planets in our solar system, we see a diversity of objects. And this gives us a hint that giant planets around other stars may also exhibit a wide diversity, although I think we don't know that necessarily at this time. Here's just a plot showing the thermal structures of Saturn and Jupiter, comparing the two and seeing how the cloud layers, especially which are illustrated, have different thicknesses. This is owing to the different surface gravities of the planets. And things like that. So thinner clouds on Jupiter explain why it has stronger contrast between bands and zones and belts, which really just gives us a sense that the fundamental properties of the planets, even though they're not that different between Jupiter and Saturn, can give rise to very different physical appearances. And so we might expect that for exoplanets. The same is true on Uranus and Neptune, which are even more similar, I think, at first look than Jupiter and Saturn should be in terms of their mass. But Uranus has this greenish color, nearly featureless, colors due to the reflectance of methane, whereas Neptune has, you can see a faint banded structure, and it has wispy clouds. This arises from slightly faster rotation than Uranus, and also that its internal heat is escaping for some mysterious reason. Again, just comparing Uranus and Neptune and now comparing to Jupiter and Saturn, like I said, these differences between Uranus and Neptune, due to differences in how the internal heat's escaping, distance from the sun, and also slight differences in the surface gravity, give rise to very different planets. And so we talk about ice giants as a class of planets, but even within our own solar system, Uranus and Neptune have very significant differences. Putting the atmospheric study of exoplanets in the context of the broader range of parameters and properties that we can measure for exoplanets is what I'm trying to do with this slide. This is just my quick single slide summary of the things that we try to measure for exoplanet systems in terms of 3 categories. We think about system architectures as a whole, that is all the planets, their masses and orbits. We think about the individual characteristics of the objects, and I list the properties that we can measure or we can hope to measure for a large number of exoplanets. And then we also compare the properties of the planets themselves to the properties of the host star, the mass, rotation, age, composition, multiplicity of the host star. So this is the whole framework for what we're looking at in terms of individual planet characteristics and where the atmosphere sits in all that. If we home in on those individual characteristics of exoplanets, we think about taking a spectrum of a planet, studying its atmosphere, measuring its composition, and studying the temperature dynamics, and potentially even the habitability. We want to put this in the context of, for example, the mass, radius, and thus density of a planet, connect that to the bulk composition and interior structure that we infer from the measurement of the mass and radius. And of course, we want to connect that because the atmosphere is intrinsically linked in terms of the formation and evolution of the planet with the bulk composition and interior structure. And then we want to also put that in the context of where the planet's orbiting in the system, what's its distance from its host star, did it form there, has it migrated or been moved there by some other process, and ultimately tie it all together in terms of an important constraint on planet formation and evolution. So the giant planets of our solar system, giant planet atmospheres are primary atmospheres. That is, they're accreted from the protoplanetary nebula. They are dominated by hydrogen and helium. And so we think in terms of solar composition gases and slightly metal-enhanced solar composition gases for Jupiter and Saturn. The same is also true for Uranus and Neptune, although the metallicity enhancement is substantially larger. These planets' atmospheres are also dominated by hydrogen and helium, but also have a very significant amount of methane, and even bordering on a level of metallicity enhancement that you could say maybe this isn't a scaled solar abundance anymore. The abundances in all 4 planet atmospheres strongly affected by condensation. For example, water, which is predicted to be an important building block of giant planets, is not observable in the upper atmospheres of any of the giant planets because it's condensed out. And so this will be an important theme throughout the rest of these lectures, is taking advantage of hot exoplanets that have water in the vapor phase, well mixed in the atmosphere, and detectable with remote observations. Clouds, as I said already, dominate the appearance of the planets, and so maybe it's not surprising that we see clouds in exoplanets, although I've personally been surprised by their appearance. And helium is deficient in Jupiter and Saturn's upper atmospheres, likely because it's raining out. And then, of course, non-equilibrium effects are very important in the atmospheres of the solar system planets and the giant planets in particular. These are much cooler atmospheres than the planets around other stars that we're probing at the moment, and so things like photochemistry and vertical mixing are also quite significant and change the abundances of chemical species in these planets' atmospheres. Here's one of my favorite new plots that came out in a paper just a couple of weeks ago that summarizes our knowledge of the elemental abundances in the atmospheres of the giant planets of our solar system. So you got Jupiter, Saturn, Uranus, and Neptune, and the elements that have been measured. We know more than any of the other planets the abundances of elements in Jupiter's atmosphere because of the Galileo entry probe that was about 20 years ago. And so this gives us access to the noble gases that we would not otherwise be able to determine the abundances of without in situ measurements. I think this is fascinating because, for example, Jupiter is seen to have a very consistent elemental abundance enhancement over a range of elements of about 3 times the solar value. And that's a very remarkable thing. From the standpoint of the formation of Jupiter, it's broadly consistent with the idea of core accretion and the pollution of the atmosphere from accreting planetesimals that are dissolved in the atmosphere. But the remarkable consistency across all these different elements and the details is hard to understand. Saturn is significantly more metal enriched than Jupiter, and then Uranus and Neptune further metal enriched, although the only proxy that we have there for the metallicity is the methane abundance and tracing the carbon abundance. In this plot, you also see some mysteries. For example, helium and neon are abundant in Jupiter's atmosphere. Helium is thought to be raining out, and perhaps neon is also being pulled out with the helium. As I said, water is going to be a consistent theme throughout these lectures, and it's interesting to note that from the Galileo entry probe, which would be our real only way to probe currently the abundance of water in Jupiter's atmosphere, suggests a water depletion in Jupiter's atmosphere. Not even solar, but subsolar. It's strongly inconsistent with the enhancement seen in all the other elements. Water is interesting because, right, it's tracing the oxygen abundance. Oxygen being the 3rd most abundant element in the universe, and a key volatile species that seeds the formation of giant planets. So this is a big mystery, and then I just point out that there's a mission called Juno that's arriving at Jupiter. Has it arrived? It's arriving, yeah, so very soon, and one of the goals of Juno is to use microwave observations to probe the deep water abundance in Jupiter's atmosphere to try to get to the bottom of this mystery. I spoke mostly about the giant planets. I just want to say, in terms of terrestrial planet atmospheres, highlight that these are secondary atmospheres strongly influenced by the loss of any original atmosphere that the planets accreted when they formed, and then also strongly affected by geophysical, biological processes, etc. Okay, so how do we observe the atmospheres of planets around other stars? Probably most people in the room are familiar with these, but I think it's useful to walk through so that everybody's on the same page. I'm going to start with discussions of transits and occultations. This is the area that I'm most familiar with, so I'll speak more in depth about this. Transits and occultations. So when you have an exoplanet that's orbiting its host star so that the plane of its orbit is perfectly aligned with our line of sight from here on the Earth, you see once per orbit the planet will pass in front of the star, and once per orbit the planet will pass behind the star. So it passes in front of the star, that's the transit, passes behind the star, the secondary eclipse. Due to this fortuitous orbital geometry, we can probe the atmosphere of the planet in multiple ways. I call the study of planetary atmospheres with transit techniques sort of the small black shadow approach, to contrast it with the pale blue dot approach, which is the direct imaging approach, that is, you spatially resolve the light from a planet from its host star spatially on the sky. With transits, we're resolving these planets temporally rather than spatially. The transit technique has a number of strengths and also weaknesses that I'd like to highlight. For transiting planets, we generally know the mass and radius of the planet. We certainly know the radius, and often we know the mass through complementary observations, radial velocity measurements, for example. When you know the mass and the radius of the planet, you know the surface gravity of the planet. That's an important boundary condition for understanding, for interpreting observations of the atmosphere. And it also gives you insight to the bulk composition of a planet. It may not uniquely determine the bulk composition of the planet, but it definitely gives you a lot of insight. So this is something that we're not going to have for directly imaged planets. The most we could really hope for is to measure dynamical masses for directly imaged planets, although that's very hard and it can take a long time. Radii have to be estimated through the influence of the surface gravity on the spectra of directly imaged planets. And so that's a particular challenge of direct imaging that we don't have with transit observations. As I said, we have multiple probes of the atmosphere when we're seeing these planets transit. We see transmission spectroscopy when the planets transit and pass in front of their host stars. We also can see the light emitted or reflected from the planet blocked by the host star when the planet goes behind its secondary eclipse. These different viewing geometries give us access to different parts of the atmosphere in terms of altitude, in terms of longitude, and they also have different degeneracies in their interpretation that are also very interesting. So you can combine these measurements, break model degeneracies, see different parts of the planets in ways that you can't do with directly imaged planets. You can also study planets that are close into their host stars. I think of this as an opportunity in the field of exoplanets to study new objects that weren't really anticipated to exist and to take advantage of these objects from being in very different physical regimes. So it's like, imagine a laboratory where you take Jupiter and put it there on a hot plate and warm it up. And it's like, you just ask the question, what happens when I do this experiment? Well, that's effectively what we're doing with hot Jupiters, right, for example. For all the strengths of the transit technique, there are a number of weaknesses, and that's why direct imaging, of course, is an extremely important and interesting technique on its own. For transits, we only measure planets relative to their host stars. That means a couple of different things. We have to, the challenge of transit spectroscopy becomes extremely high temporal precision rather than very high spatial resolution and contrast. And so that's its own kind of challenge. Another thing is we only understand the planet as well as we understand the star. All of our transit measurements are relative to the star. For example, the transit depth is the size of the planet relative to the size of the star. You don't know the size of the planet in the absence of accurate information about the star itself. Transiting planets, of course, limited to the most part for planets that are transiting, and I say for the most part because these temporal techniques for resolving the planets in time rather than spatially have also been used for non-transiting planets in a limited fashion. But for the most part, we are limited to planets that are transiting, and so that's only a subsample of all known exoplanets, right? Even for a hot Jupiter, the transit probability is only about 10%. So you can only, in the best case, imagine that we're looking at 10% of all known hot Jupiters. We're also limited to close-in planets, and so I think studying the atmospheres of planets with transit techniques is really limited to planets that are closer than 1 astronomical unit and probably much closer than that. Say with orbital periods on the order of a few tens of days. It's hard to imagine doing transit spectroscopy observations of exoplanets with orbital periods longer than that. So direct imaging gives us access to the outer parts of planetary systems that transit techniques cannot access. So complementary techniques, transits and direct imaging with unique strengths and weaknesses. So let's start with a discussion of emission spectroscopy, which is actually what happens when you see the planet go behind the star. At secondary eclipse, you're seeing the light from the planet be blocked. And so this depth of the secondary eclipse gives you information about how much light the planet is either emitting or reflecting. If you're talking about reflected light at short wavelengths, you can approximate this planet-to-star flux ratio, which is really the depth of the secondary eclipse, is due to the geometric albedo of the planet, the size of the planet, and how close it is to its host star. There's a phase function that comes in here that's relevant for direct imaging that pops out when you're looking at secondary eclipse. If the thermal emission is dominating, say at infrared and longer wavelengths, then you're really probing the temperatures of the planet. And so the planet-to-star flux ratio is equal to the ratio of the sizes of the planet to the star squared. And then you can imagine the planet and the star just emitting as black bodies at whatever wavelength you're looking at with some characteristic temperature. Just to give you a sense of the size of the signals involved here, a hot Jupiter measured in thermal emission at infrared wavelengths orbiting a sun-like star has a planet-to-star flux ratio of about 10 to the minus 3. So that's the secondary eclipse depth on order of 10 to the minus 3. Here are some simulations, some theoretical models of the expectations for the thermal structure, that is the temperature-pressure profile for hot Jupiters, and the emergent spectra from those planets from Jonathan. Here we're showing how the thermal structure and the emitted light changes as a function of the properties of the planet. The most important property of the planet is simply the temperature of the planet. And here's a range of short period hot Jupiters that these models were calculated for. And then the emergent spectra here showing how the planet-to-star flux ratio generally increases to longer wavelengths, because if you imagine the planet and the star behaving as black bodies, the planet's cooler than the star, the planet-to-star flux ratio then will be larger at larger wavelengths, longer wavelengths. And so this gives you just a sense of the diversity of the thermal structures and the emitted light from these planets that we're expecting to try to determine. Here are example data for the kinds of measurements that we try to make. This is an example of a hot Jupiter, WAS-19. It's a very short period giant planet, hot giant planet. We're measuring the secondary eclipse as a function of wavelength to produce the spectrum of the emitted light from the planet. So these are secondary eclipse light curves. These are ground-based observations, so a little bit noisy, but it gives you a sense of how challenging it is to measure even the largest signals for hot Jupiters on order of 10 to the minus 3. So if we can make these measurements of secondary eclipse depths, this is also observations these are space-based observations made with the Spitzer Space Telescope at longer wavelengths, and you can see the quality of space-based data far exceeds ground-based data in general. And so putting these observations together, what we hope to do is measure the secondary eclipse depth as a function of wavelength and produce this spectrum of the planet, and the spectrum of the star is factored in here, and then compare to models and try to retrieve things like the temperature of the atmosphere and the abundance of molecules. I started with secondary eclipse, but when you think of transits, you think of the primary eclipse or the transit itself. And so we can probe atmospheres with this technique known as transmission spectroscopy when the planet passes in front of the star. The key thing here is that the limb of the planet is fuzzy, and the fuzziness depends on the wavelength of light. And what happens is you have light from the star filtering through the outer annulus of the planet while it transits, and depending on the wavelength, the absorption in the planet's atmosphere will be higher or lower, and thus the light from the star will be blocked higher in the atmosphere or lower in the atmosphere. And so the apparent size of the planet will change as a function of wavelength due to the opacity in the planet's atmosphere. So the depth or apparent size of the planet depends on the wavelength of light. Here are some theoretical predictions for transmission spectroscopy signals, also from Jonathan. These are hot Jupiters. These are giant planets with a range of temperatures. The key thing about transmission spectroscopy is that absorption in these figures is always up because the planet appears larger where you have wavelengths of strong absorption. And so we plot, the convention is to simply plot either the size of the planet or the transit depth here on the y-axis, and then larger values are up. The planet appears larger. That's at wavelengths where you're having strong absorption from molecules or atoms. So size of the planet as a function of wavelength, and then models for a range of temperature. You can see how the predictions from the models change with temperature. You can see different molecular bands that come and go. Two things happen here as you change the temperature. As you go down in temperature, the scale height of the atmosphere decreases, and I'll say something about that in a second, and thus the features become more and more compressed. Also what happens is the chemistry changes, right? So you go from very hot planets that may have titanium or vanadium oxides to cooler planets where those condense and fall out of the atmospheres. You then start to see alkali metals giving rise to lines in the optical, and then those also condense out, and then you don't see them, and now you see things like methane. So temperature is strongly driving how transmission spectra appear through multiple effects. Again, we're measuring these signals as a function of wavelength. We're measuring light curves as a function of wavelength. So these are example transit light curves now. These are much larger dips because you're seeing the whole planet pass in front of the star. For hot Jupiters, or this case is a super Earth around an M dwarf, the transit depth is on order of 1 or 2%, but you're still looking for that very subtle signature on top of the transit depth that indicates the presence and detection of the atmosphere. So you're still looking for fairly similar size signals, 10 to the minus 3, or smaller size signals on top of the transit depth. As I said a second ago, the transmission spectrum of a planet depends on this thing called the scale height, which just gives you an estimate of how puffy the atmosphere is, right? That's one E-folding length of pressure in the atmosphere. You can calculate the scale height according to this formula. It depends on the temperature, the mean molecular weight of the atmosphere, the surface gravity of the atmosphere. The size of features in transmission spectra can be approximated by this formula, where the change in the depth of the transit as a function of wavelength depends on the size of the planet, the size of the star, the scale height of the atmosphere, and then some multiplicative factor, where the proportionality factor depends on the strength of absorption at whatever wavelength you're talking about, and the resolution of the instrument that you're using to take the data. This cartoon here gives you a sense of why low density, large scale height atmospheres, either because they have low mean molecular weights, high temperatures, or low surface gravity, give you larger features in transmission. It's just because the area of the planet's atmosphere that the starlight has to interact with is just larger. So you're dealing with simply a scaled up version. So this is puffy, extended atmosphere, or low, high density, sort of compressed atmosphere. I want to highlight this idea of the proportionality factor in this equation. This had been, say, 10 years ago, numbers had been thrown out saying, oh, you'll cross, say, 5 scale heights or even 10 scale heights in a hot Jupiter atmosphere, going from one wavelength where you're seeing the continuum to another wavelength where you see strong absorption. What we've seen, though, is that that's definitely not true. I don't think we've seen any planet where we're seeing signals of order 5 scale heights. The truth is more like 1 or 2 scale heights in the best of cases. So if you want to use this formula to approximate the size of signals, I encourage you to consider the number 1 or 2 in front of this equation as the proportionality factor rather than 5 or 10, which had been used before. And then I also want to highlight the importance of the resolution you're talking about. Of course, if you measure from the continuum to the core of a line, you'll see one size signal. But if you've smeared that line out because you have low resolution observations, as we typically do, then this proportionality factor goes down. So at the resolving powers that we're using now with current instruments, say on order of 50, you're only probing 1 or 2 scale heights in the best of cases. You can calculate more precisely the change in the altitude that the light's being absorbed in a planet in transmission with this equation, which I give you the reference for here, and the caption here tells you what the different terms are, and I've made a slight correction. It's not the elemental abundance that changes the absorption, it's the actual chemical species, and that's not necessarily an element. It could be, and most likely is, a molecule. But you can see some of the familiar terms here, the kT over mu g from the scale height, the size of the planet comes in, and then you have the absorption cross-section and the abundance of the species. Careful study of this formula illustrates one of the degeneracies that exist in transmission spectroscopy, which is that to first order, the thing that you get out is the partial pressure of the absorbing species rather than the total pressure. And you actually don't know the total gas pressure in the part of the atmosphere that you're probing, which means that getting absolute abundances of the chemical species is challenging. That's the first order, and I'll talk in the third lecture on Friday about how we move past that, because I consider that one of the most important open questions in this field of exoplanet atmosphere characterization moving forward. Here are some more simulations of what transmission spectroscopy look like, and now we're comparing these theoretical models to real data. So these theoretical models of the sodium D doublet and the optical are extremely beautiful, and then the data I also think are beautiful, but maybe you think are less beautiful. Instead of resolving at infinite resolution this beautiful double peak doublet, instead you get 1 point integrated over this dashed line. Right. So it's importance of considering the resolution of the data that you're trying to interpret, and what you can pull out of that is kind of the crux of the situation. So this is the first detection of exoplanet atmosphere, for those of you who don't know, Charbonneau et al. 2002 for HT 209458b, observing the sodium line. And this is the detection. It's 1 point, it's 4 sigma difference from the continuum. Clouds play an important role in sculpting and changing the visible appearance of the planets in the solar system, and they also play an important role in exoplanet atmospheres. And they're particularly important for transmission spectroscopy because you have a slant viewing geometry through the atmosphere. Right? The planet's in front of the starlight's going through at a grazing path. And so while at a normal viewing angle, the integrated opacity from a cloud could be low, you have factors of, say, 50 increased path length when you're looking at transmission. And so the influence of clouds are much larger in transmission than they are in the normal viewing geometry of secondary eclipses or even direct imaging spectroscopy. And so these are just figures, again, from some of Jonathan's papers showing temperature pressure profiles for example planets, and then the dashed curves are condensation curves for different cloud species. And unless you're already working in this field, these are maybe species that you've never heard of, like zinc sulfide, and things like that. But this just tells you that these are all hot Jupiter, I think, calculations, how rich the cloud chemistry could be and the very wide diversity of clouds that could exist on even hot Jupiters, and thus could give very different signals in the spectra of these objects. So I've talked about secondary eclipses, I've talked about transits, but there's another thing that you can do, which is that if you observe the planet not just during one of these short events, but during the entirety of its orbit or large portions of its orbit, then you can see how the light emitted from the planet changes because of the planet's rotation. For short period planets that we're probing now, these are all tidally locked, or almost all tidally locked planets, which means that you get this scenario here, where you have a permanent day side, a permanent night side, and the planet revolves or rotates once per revolution. And so you see the changing illumination of the planet as it orbits. And so if you don't just look in secondary eclipse, but you observe through the entirety of the orbit, then you can see this rotation of the planet through the change in the appearance of the hot and cold sides. Okay, this is of course called phase resolved or phase curve observations, either photometry or spectroscopy. First done, well, not first done in 2007, but I'd say the real standard setter was done in 2007, observations of HD 189733b, a hot Jupiter, observations of half an orbit from secondary eclipse, from transit, to secondary eclipse, and this is the zoom in here, showing the sinusoidal variation as you go from the night side of the planet, which is seen near the transit, to the hot day side of the planet as it rotates into view half an orbital period later, and then the secondary eclipse. Turning this sinusoidal variation into a temperature map of the planet as a function of longitude, they've just made a guess at the distribution in latitude, made this map, temperature map of the planet. There's a little movie for those of you who want to visualize what this looks like. Probably you've seen this kind of thing a million times, but just in case you haven't, you're seeing, right, the tidally locked planet, permanent day side, permanent night side, right? And around transit, which happens now, you see the night side of the planet, half an orbital phase later, you see the day side, the hot permanent night day side of the planet rotate into view. So you expect to see this sinusoidal variation that the strength of the size of this sinusoid depends on how much heat is being redistributed from the hot side to the cold side. And then you want to compare this to theoretical models. For example, models calculated with a general circulation model. This is just showing an example of one of those kinds of models for a hot Jupiter, where you're showing the temperature map, wind speeds are given by the size of the arrows, and longitude and latitude for a cut through the atmosphere at 1 bar. And you can see, for example, for hot Jupiters, this prediction of the hot spot shifted downwind because of an equatorial super-rotating jet. This is the kind of thing that's already been confirmed from observations. Okay, so I want to talk about some of the challenges. I've talked, now about the basics of the observations that we try to do and the data that we try to get. What are some of the challenges of making these observations? And this is really just kind of an overview of the kinds of challenges with some specific examples that I'm familiar with. So I'm listing here challenges of transit observations. After this, I'll talk about the basics of direct imaging and similarly challenges of direct imaging. Okay, but for transits, I've listed a few things here, and this is probably not an exhaustive list, but this will give you a sense of the challenges that are faced. One is simply collecting enough photons. Right? This is a measurement of a signal in time. You're resolving the planet in time, and you have to achieve the precision necessary to distinguish changes that happen over time. And so in the simplest case, you imagine a photon counting limited measurement. And if you just work through the numbers, how many photons do you actually need to accumulate to make measurements at 10 to the minus 3 or better, and ideally better? It's a large number of photons. And so a lot of instruments were not designed to do this. In fact, none of the instruments we're doing transit spectroscopy observations were designed to do this. And sometimes you can run up against characteristics of the instruments that prohibit you from making full use of the collecting area, for example, of a large telescope. One prominent example is the use of the Wide Field Camera 3, which is really the premier instrument for transit spectroscopy these days, the Wide Field Camera 3 or WFC-3 instrument on the Hubble Space Telescope, installed in the last servicing mission now 7 years ago. The Wide Field Camera 3 was designed in the late 90s and early 2000s to look at faint galaxies at the edge of the observable universe. And that obviously is a very different photon counting regime than stars a few tens of parsecs away. And so there's a challenge for WFC-3 observations in that the electronics on board the instrument can only hold a few full-frame images from the instrument before observations have to be stopped and the data have to be transferred to another part of the memory and the electronics on the telescope. And this stinks, and I'll say why in a second. But people working in this area have been very clever, in particular people at the Space Telescope Science Institute, which runs Hubble, in developing this new technique called spatial scanning, which allows you to, while you're taking exposure of a star, and you're taking a spectrum, so normally the spectrum would run along here, and would have a full width half maximum of about 2 pixels. Instead of taking just a few of those images and then having to wait while those data are transferred to another part of the electronics, during one exposure you can scan the telescope in the spatial direction, up or down. And so as you go, smear the light out in the spatial direction and take advantage of all this empty real estate on the detector. This is only a quarter of the width and height of the detector. So there's a huge amount of detector here. And so you can integrate for much longer with this technique without saturating the detector, collecting a huge number of photons, and making high precision measurements. So this is an example from a paper that Laura led a couple of years ago. These are observations at GDAY 1214b, but this is just representative of observations with WFC-3 using this spatial scanning technique. Again, making these chromatic light curves, dividing the data up as a function of wavelength, and integrating as a function of wavelength over the spatial direction, all these photoelectrons that have been captured. The reason why we want to do this, you may think it's a cardinal rule of precise telescopic observations to not change anything, and it is, and I would rather not to be doing this. But it's unavoidable because otherwise, these are similar observations at GDAY 1214b and GDAY 1214, the host star, where you can take just a few exposures before you have to stop for 5 or 6 minutes and transfer the data to somewhere else, and then you start your exposures again. So this is a single orbit of the telescope, which normally you would want to integrate this whole time. You want to make just lots of observations over there, not take these breaks. These breaks are because the telescope's going around the Earth, and so those are unavoidable. But these are because of the detector electronics being pretty old. So the spatial scanning, instead, you can't really see here, but it allows you to make just continuous integration over the whole visibility period that the star is visible to the telescope. So from the standpoint of the duty cycle, it's obvious why we want a spatial scan. You don't want to just interrupt your observations. You only have a certain amount of time to get the data during the transit or a little bit out of transit to set the baseline. Another more subtle thing that happens is that your detector systematics actually reset because you're not reading the detector out regularly like you were. And so that's exhibited, you can see this sharp rise in these different samples, right? From the beginning to the end of the sample, there's a rise up. And so that's set by detector persistence that's then reset every time you stop integrating. Okay, so I think I've said enough about that. So being clever about just gathering enough photons is really the first order of business in this game sometimes. Another thing that can prevent high precision measurements, even if you've gathered enough photons, is maintaining a constant flux level as a function of time. And one thing that can change that is whether you have aperture or slit losses. These are slides from a presentation I gave a number of years ago, but just illustrates the idea of what I mean by slit losses. These are observations, this is a case study of observations done from the ground, where I'm trying to use the observations of a comparison star that's nearby on the sky to correct for variations in the Earth's transparency. So we have our target, this was case HAP-P1, and I put a slit on both of these stars, and they're separated, they're very close on the sky, so this should make an ideal comparison star. And I took some transit observations. And so this is what I got. And there's two categories of crappy data in here. There's one category where the guiding was bad, and I know the guiding was bad because I was sitting there looking at the computer that's showing the guiding. I'm like, the guiding's bad. It's that easy, right? I'm a real genius. The guiding's bad, right? The telescope's just wobbling all over the place. Well, there was another way of guiding, and then we switched to that way of guiding. The data got a lot better, but still, you can barely see the transit. And this is, a 2% dip, almost 2% dip, and I'm trying to measure 500 ppm on top of this 2% dip. So what's happening here is that the guiding is not perfect still with this better guiding. And then also seeing variations. And what this means is the stars are just kind of bouncing around in these slits. And a normal stellar spectroscopist wouldn't care so much about this because they only care about the relative flux over very short wavelength sections. But I care about maintaining the flux level constancy over the course of hours. And so this thing where I've drawn the slits kind of in gray, imagine the telescope's just kind of doing that a little bit and the seeing's changing. The stars are dancing around there. So this is one of the things that I did, which was to study this problem in detail and ask myself how big these slits have to be, for example. 12 arc seconds turns out to be a good magic number. When I go from 6 arc seconds to 12 arc seconds, the data get way better. And this is the kind of data that you need to get to actually start constraining the atmosphere. And I'd say start constraining. I mean, this is not JWST level kind of data. So this just gives you a sense of the kinds of things that you have to look out for, these aperture or slit losses. Let's go with Mike first. Yeah, but you got background. Well, you have to block out other light. If you're doing it in the infrared, you've got a substantial background that you want to block out. Yeah. And there's simply art spectrographs that allow you just to take observations without a slit from the ground, because it's the crazy thing to do.
How big would the slit be that you would get contamination from ours?
It depends on where the other sources are. I mean, you make the slit bigger, you're just getting more and more background, which becomes another noise source. Well, this is a characteristic number that's useful for ground-based observations. Well, then you would have substantial background contamination. That's still also. It's not really, I don't want to give you the sense of the number. I just want to share this concept because the number changes in every situation. Depends on where you're observing from, what the conditions are that night, ground or space, for example, because you have this issue in space. And I'm highlighting this because we're not finished with this. WIFC3, which we use on Hubble now, is a slitless spectrograph. And so that works great in space. The background's a lot lower. But a few of the instruments on JWST that people are thinking about using have entrance apertures of one sort or another. For example, NearSpec has, it's a square aperture. And it may be big enough so that you don't have slit losses, but it's always tied to, what's the change in. The issue with slits is that the star is not centered perfectly all the time. If it were centered perfectly all the time, the slit losses were the same all the time, it wouldn't be a problem. The point is stuff moves, right? And so the pointing jitter, for example, in JWST, coupled with the size of this aperture, makes me wonder whether that will work at the level people are expecting it to. Another thing are like integral field units would have lenslet arrays, will also have this issue. So anything with any sort of aperture, you have to think carefully about this. So they're really just an illustration of this general problem that you have to think about. You can't just blindly say, we get a new spectrograph on a giant space telescope, and it's going to work great. This also ultimately led me to develop this technique of multi-object spectroscopy from the ground using not just wide slits, but using multiple comparison stars. And these were observations of GJ 1214 that were obtained with that technique. Okay, so aperture slit losses. Another thing to watch out for, pointing variations combined with inter and intrapixel sensitivity variations. I really should have said for the second point, pointing variations plus slit losses, because it's really the time variability of the slit losses that's important, and the time variability comes from the pointing variations. So let's talk about inter and intrapixel sensitivity variations. What I mean by this is interpixel sensitivity variations. Let me get this right. Intrapixel sensitivity variations are variations within a given pixel between, say, the center and the edge. Interpixel sensitivity variations are variations in the sensitivity between pixels. These are different effects, but they manifest similarly when you have pointing variations that move the image of the star over these different pixels. And so this is just an illustration of that, showing this is I think the pointing histogram for a Spitzer observation. This shows the pixel this is the intersection of 4 pixels. This is the pointing map for a Spitzer observation of a transiting exoplanet. These are secondary eclipse observations. The color here represents how much time you've spent there. And so it's pretty well constrained here on the edge of the pixel, but you can see it's drifted, spent a lot of time drifting around that too. And then this color map shows the sensitivity variations that are then mapped by that. And you can see substantial sensitivity variations in this area that's been covered. And so this manifests for Spitzer, in particular with IRAC, it had this cycling pointing variation caused by the heater on one of the mirrors going on and off. So this 30-minute or even an hour-long pointing variation, moving the PSF of the star over these different sensitivity regions gives you these systematic effects in the data that have to be corrected.
But is this intra or is this
Well, yeah, because this is the edge, so it's both. It's both. I mean, they call it intra because the pixel sampling for Spitzer IRAC is pretty much all the lights on 1 pixel for the most part. But really, it's both, right? And you see that as you cross this pixel boundary, you see it's not as obvious here, but you would see it in other ways. And it depends on the detector technology and all this stuff. Because you talk forever about this, but right. Just the point is you have sensitivity variations in your focal plane. If you change the pointing, right, that's going to manifest as systematics in the photometry or spectroscopy. Yeah, I have to say I don't know what the origin of that is. What I've seen are maps starting in a center, moving to the edge, and seeing a normal fall off there that you can sort of imagine from the manufacturing standpoint. Here, I'm surprised it's that continuous across the edge. I can't pretend to understand where that's coming from. It could be that it's an artifact of how they're actually analyzing the data. Right? It could be that that's not actually real, that that's just some sort of approximation that allows you to flatten this out, but really it's not, what's going on. So this is right. That's the challenge, right? It's not just having that; it's then trying to have to correct it and never being certain about what's going on. So this is the kind of thing we could expect again to see with JWST. There are going to be pointing variations. There are going to be intra and intrapixel sensitivity variations, and we're going to have to deal with this. Hopefully, they're lower than what we've dealt with before. Probably they will be. But a lot of the detectors in the JWST instruments are not very different from what we're already using now. So this is going to be an issue. Yeah. You'd have to ask a Spitzer expert, which I'm not. I think it is. I think the answer is yes, but I can't give you a definitive answer on that. Yeah, Mike? Yeah. So they've tried to do this, after the fact with Spitzer, with so many observations in one general area, but the pointing is not that bad that you've mapped the whole focal plane right over the course of the mission. You end up with like little spots of coverage here and there, and you can't put the data, you can't put the PSF right back on the same pixel at the 100th or 10th of a pixel level necessarily. So, and then the detector performance could be different in space than it is in the lab. It would be good to do that, but I'm not sure. It didn't get done for JWST. It's not going to get done, and so we're just going to deal with it. Detector persistence. Let's just keep running through these. Detector persistence is another issue. These are, again, this is a figure from one of Laura's papers showing this ramp up, which we saw before, but now on a larger scale because we have these continuous observations. These are HST WIFC3. This is the Mercad-Tel detector, Hawaii 2 detector, where you have, so detector persistence. You have impurities in the photosensitive material in the detector. So you've got light coming in and it's turning that into electrons, but some of those electrons get trapped in the impurities. And so when you read it out, you don't get all the electrons out that have been created from the light coming in. These charge traps, so-called charge traps, get filled as your observations go on, which means that as time goes on, you get more and more of the electrons out that are being produced by the light coming in as the charge traps become filled. So that's why there's this ramp up here. And it should asymptote to a constant level, although we haven't necessarily seen that. And so this is another thing that has to be corrected. This will almost certainly show up in JWST observations. it's a challenge for HST observations because we have these unavoidable gaps. And so it resets to some extent. The charge straps, the time scale for filling the charge straps is really short compared to the time scale of releasing them. But the release time this is 45 minutes, and it has to be on order of 45 minutes. Some of those electrons start leaking out, and you don't see those, but what happens is you now have empty charge straps. So you have some fraction of charge straps that were filled here that are no longer filled here. And so this is a challenge, again, of the data analysis, is that you have to try to account for this. Detector persistence. If you're observing from the ground, you have issues with the transparency variations in the Earth's atmosphere, and contamination of specific wavelengths. Transparency variations are what I showed, or what we're trying to correct. For example, here, these are observations of GJ 1214 with wide slits, so there are no slit losses, but every little bump and wiggle here is because of short timescale changes in the transparency of the Earth's atmosphere. Observing reference stars mitigates this to some extent, but not perfectly. You try to divide this out, and you get something that's fairly flat, and add some other correction, and you get a nice light curve. So that's telluric transparency variations. But you can also get contamination at specific wavelengths, which is part of the reason we go to space, right? There's some wavelengths, for example, the water absorption bands in the Earth's atmosphere. You just don't get light from outer space through those. And thus you can't see those spectral features in an exoplanet's atmosphere. This is illustrated here with observations at high resolution, VLT CRI-RES observations. These are spectra in wavelength, and this is a sequence in time. So you're seeing these telluric lines. These are just pure absorption by the Earth's atmosphere. And then with this high resolution technique, they're trying to mask those and clean those out, and they have this process for doing that. But that also is a contamination factor. And so that's a chief challenge of using high resolution observations, for example, is removing these telluric lines and not confusing those with the lines from the exoplanet. Limb darkening is a particular challenge that I'll highlight as well. Limb darkening is something that happens in transit observations when the planet goes in front of the star. The star is not a uniform disk. It's brighter in the center. It's darker on the limb because it's a three-dimensional object. Limb darkening can manifest itself as features in a transmission spectrum if you don't take care of it properly. Here's the best example I know of that. Again, another result from one of Laura's papers showing the derived limb darkening coefficient as a function of wavelength and comparing it to the predictions of different theoretical models. This is for the star, right? The point being that it looks just like the absorption signature of water because this star has water in its atmosphere. And so if you have the limb darkening wrong, you'll get changes in the transit shape that mimic changes in transit depth that you may think are due to the planet. And so this result, I think, is really nice because we were able to pull the limb darkening from the data themselves and simultaneously with the signal from the planet. So this is a purely empirical measurement of what's going on, which to me is the best thing. We cross-checked with the theoretical models, and it agrees very well with our expectations. But you can see how the challenge is if you didn't know the temperature of the star just right, or there was some systematic in your model atmosphere, meaning you got the temperature of the star right, but there's an error in the model atmosphere, you could get these limb darkening wrong if you were trying to fix that from the model, and thus get a spurious signal in the transmission spectrum. So this is, for me, highlights why more data are always better. And I typically try not to make observations of just a single transit, for example. It's because I like to pull the limb darkening out of the data. Stellar activity is also a big challenge, again, primarily for transits. Here's a result for a really canonical planet. This is HD 189733b, which for the longest time people thought had this characteristic lambda to the -4 change in its transit depth or apparent planet size, indicative of Rayleigh scattering from haze in the atmosphere. However, Peter McCullough and colleagues have studied this in detail and found that this slope, which is actually covering many scale heights, could also be caused by unocculted star spots. So that is, the planet's, the stellar surface is not uniform in brightness, and it's changing in time because spots are coming and going. And so, well, it's not the change in time that's important, it's the chromatic effect. That is, the planet's crossing a part of the star that has a certain brightness, and then the rest of the star has a different brightness. And that brightness ratio between the part of the star that's being covered by the planet and not has a wavelength dependency because you're looking at different temperatures, spot versus not spot. And so this slope here could also be caused by spots. So here's the caption. You can read all about this in the reference. So stellar activity can also mimic signals, and it's particularly important in transit. It's less so at secondary eclipse. And then mystery effects. Yes?
Quick question about that. If you observe it multiple times, maybe scanning will always give the same thing. But something like sunspot, isn't that random variation if you observe multiple times?
That's a good point. That's a good point. Yeah, I don't know if that's been looked at. I mean, stellar activity, this is one of the manifestations of stellar activity. Another one would be if you're trying to build up a composite spectrum over different wavelengths and the stars changing with time between your different observations, that can have an impact. But actually, that's a really good point. I'd never thought about whether this slope should be different at different epochs. And it is pieced together from different observations at different times. So I wonder, that's a really good point, actually. I don't think anybody has thought about that. Oh yeah, wow, okay. Is it consistent with this idea of the changing spot coverage on the unocculted part of the star? At the overlapping wavelengths? Or propagating this lambda to the -4? Okay. Okay, wow. So that could be further evidence that this is actually not Rayleigh scattering. If it's changing in time, or if the steepness changes with different instruments that we're observing at a different time, could be the stellar activity. And then, so the last category of things that can bite you in terms of transits are just mystery effects, and this is the worst thing. These are like Jonathan's unknown unknowns. Mystery, they're mystery. I call them a mystery effect because they're mystery. This is one example from a paper from Kevin Stevenson. These are ground-based observations with GMOS and Gemini. It's got this weird thing, it does this, right? Like, what the heck is that? We think, our guess is that this is a polarization effect, and the telescope's rotating, the polarization is changing, and it's giving this, but we don't have a real model for that. So you try to correct it, you try to model it, you try to understand it, but like in the end, that's going to be limiting your observations. Here's another result from another one of Kevin's paper. This is HST with C3. We've talked about these ramps. Some people call them hooks. But another thing that happens is this slow, steady decrease. And it's not linear. It seems to have a higher order term than linear. We have no idea where this is coming from. And this is really important, for example, for detecting shallow transits that may or may not be there, because this paper was actually about searching for the transit of a planet we didn't know if it was there or not. And whether this is linear or whether there's a sort of higher order polynomial happening here changes whether this should be up or down according to the transit depth. It's also relevant for longer duration observations to do phase curve observations. You're trying to measure a sinusoid on top of something that's doing this intrinsically. Again, we have no idea where this is coming from. These are the things that can bite you. Okay. Let's change gears. I have about 22 minutes, right? Yeah, okay. So this is great. I'm on time, I think. So I spent a lot of time talking about transits and occultations. I'm going to spend a little bit less time talking about direct imaging because this is not my area of expertise. Fortunately, there are people in the room. There are experts. For example, Andy Skimmer is there in the back. Hi, Andy. I'm going to volunteer you to be the local expert for direct imaging over the next 6 weeks. I hope that was okay. I didn't clear that with you. But yeah, it looks like it's okay. Great. So I'll say some stuff, some of which may be wrong, and then maybe Andy will correct me if I'm not right. Anyway. Okay, cool. Mike is in the audience? No, but he's in town. So direct imaging. Direct imaging is exactly what it sounds like. It's the classical picture of looking for an exoplanet around another star. You look up at the star, you look off to the side, there's the point of light. And so here I'm just showing really the classic example of direct imaging, planet detection, HR 8799, 4-planet system, all orbiting in the same direction, probably coplanar and perhaps in resonance. Really fascinating system. The challenges of direct imaging are related to the observables. So we talked about the challenges of transits in terms of having high precision as a function of time, and then perhaps difficulties in interpreting that signal, stellar activity, and things like that, instrumental effects. In direct imaging, there's really two challenges. And so that's the separation challenge, which is planets are orbiting their stars at even tens of AU. That projects out to less than an arc second for stars in the field. And then the contrast ratio. The stars are so much brighter than the planets. And so it's not one or the other of these, but it's the combination, right? It's achieving high contrast at small angular separations. That's the challenge of direct imaging. To give you a sense of the problem, showing here the intensity, this is the sun approximated as a black body, and then spectra of the Earth. And this is approximated, I think this is, I can't remember, but this is the actual spectrum of the Earth. You can see as a function of wavelength, the maximum, the minimum contrast from the Earth to the sun is on order of 10 to the minus 9. These other lines are zodiacal light, which I'll talk about in a second. So this is, in some sense, a much harder problem than the transit problem. Our instruments are much better at achieving, say, 10 to the minus 3, 10 to the minus 4 flux constancy as a function of a few hours, as they are of resolving 10 to the minus 8, 10 to the minus 9 contrast at sub-arc second resolution. Direct imaging most often focuses on young stars, and we can understand why that is because the evolution of substellar objects, whether we're talking about brown dwarfs or planets, these objects cool and fade as they age because they have no strong internal source of energy to maintain their luminosity. This is a classical plot of the evolution of the luminosity as a function of age for objects with a range of masses. Adam Burroughs' classic reference gives these in solar units, and just to remind you the conversion, the sun is about 1,000 Jupiters. So objects change in their luminosity by orders of magnitude from 1 million to 100 million years. And so direct imaging, which is trying to find objects with the largest or the smallest contrast, look for the brightest objects at these younger ages. And so observations are also done, need to be targeted at specific wavelengths because the planets are nothing like black bodies. Here again is, I can't remember where this reference was from, but this is a plot from Adam Burroughs showing predicted spectra of objects as a function of wavelength, as a function of age as well, but I want to highlight here how deviant these objects are from black bodies and how observing at a particular wavelength makes a big difference, right? This is a log scale. Orders of magnitude changes in flux, whether you're in or out of a molecular band. And then this so-called 5-micron window into the deep atmosphere probes hotter temperatures because lower opacity there can give you orders of magnitude gain in contrast. And so you go to young stars, young planets, because they're brighter, and you do observations in the infrared, and you try to target observations at given wavelengths where the planets are brighter. Okay, the technical challenges for direct imaging, I broke them up into 5 categories. One is a fundamental limitation of using a telescope to observe a star and a planet. And so that's the diffraction limit of a telescope. This is the classic formula for the diffraction limit of a circular aperture, where you have, here are I give you the units and everything here. This is probably something you've seen before. I just want to home in on this concept of lambda over d, because this term gets tossed around a lot, especially in the context of future high contrast imaging missions in space that NASA is designing. It's like, what's the lambda over d? How many lambda over d are we talking about? Because it's related to the size of the telescope, the wavelength you're looking at, and the fundamental diffraction limit of the telescope, which you can't beat to resolve 2 point sources. The diffraction limit arises because you have this finite entrance aperture that converts plane waves into spherical waves, and then the impact on your detector focal plane gives you this airy pattern. And you can calculate the ratio of from the angle from the center to the first minimum. You can calculate the full width half maximum. It's related to this lambda over d. And so direct imaging instruments are really characterized by how well their contrast, what performance they reach, what's the contrast level they reach at some lambda over d, say 2 lambda over d, 3 lambda over d. because that sets the lower boundary in terms of the fundamental performance of an instrument. Just to give you a sense of how hard this is and the impact of just pure diffraction on resolving a faint point source, I've done a calculation here where I've put a second peak to this first peak, which we can imagine the star. The second peak imagines the planet with a contrast of only 10 to the minus 4th. This would be a very bright planet relative to the star, and it's at 2 lambda over d. And can you see it? No, on a linear scale you can't see it. And so if you look here at a log scale, it's even hard to see because the diffraction pattern from the bright star even overwhelms the signal from the fainter object. So this is just a really simple cartoon picture kind of how difficult this challenge is of telescope diffraction. Yeah?
The area pattern you drew, how close to the actual observation?
Probably not very close.
It's not like you can just snap it off.
No, that's definitely true. I mean, that's the point, is you try to suppress the starlight either by blocking it or you can try to do some PSF subtraction or maybe even both. But the PSF, which is, imagine, that's what I'm calling this area pattern, right? It doesn't change with time. If you're observing from the ground, it's changing because of the Earth's atmosphere. It's changing because the instrument is changing in temperature. The optics are becoming misaligned. Things are rotating. There's all sorts of things that are happening. So the PSF is not constant in time. Point spread function, which is just basically the area function. The area function, right, is just the pure diffraction limited. The PSF is also incorporating all the other imperfections in the optical system in that. And so PSF subtraction is a technique for analyzing direct imaging data, but the fact that it doesn't work perfectly because the PSF is not stable at that level is part of the reason why you have to develop better and better systems to control that PSF better. From the ground, you've got atmospheric turbulence that further limits your ability to work at the telescope diffraction limit. This is just a very simple cartoon picture, right? You've got parallel wavefronts entering the Earth's atmosphere. Turbulence in the Earth's atmosphere perturbs those wavefronts, and then the time scale is extremely short. And so if you took a short integration, you could get this speckle pattern. And integrate over a longer period of time, say a second or longer, you get this classic PSF, a seeing limited PSF with a full width half maximum on order of an arc second or half an arc second on a good site on a good night. So this is corrected, of course, using the technology known as adaptive optics. You use these flexible mirrors and a closed control loop where you're measuring the changes in the wavefront and you're trying to correct those. Just a classical picture of a short integration with AO off. You get this sort of smeared out speckle pattern, and AO on allows you to resolve that into two separate point sources, correcting to some extent the atmospheric turbulence and potentially aberrations in your instrument. So starlight suppression, so telescope diffraction, atmospheric turbulence are really sort of the spatial resolution part of this. Starlight suppression is really the contrast part of this equation. How do you block the light from the central star so that you can see fainter point sources very close to it? And so a main technology that's used is the so-called coronagraph or occulter. Here's an example of the classic Leo coronagraph, where you have a telescope pupil, you put an occulting spot in the image plane, re-image the pupil, and put another Leo stop there, and you create this final image where the light from the star has been dramatically suppressed, and then you can see fainter point sources. Their coronagraphs come in internal and external versions. This is an internal version where you would have the occulting spot and Leo stop internally in your camera that's behind the telescope. The external version is sometimes called star shade, where you have this free-flying occulter at some distance that's blocking the light from the star. So this is not something that's been done, right? Coronagraphs are in wide use. The idea of a star shade is really a theoretical concept that people are trying to develop this technology and use. And for example, you may be able to upgrade a future space telescope with this kind of thing to improve its direct imaging capabilities. This cartoon gives you a sense of the scale of this. For example, for JWST, if you wanted to equip it with an external occulter, the star shade, it would have to be flying freely 30,000 kilometers from JWST. And it would have to have a diameter of about 40 meters. You think 40 meters is not very big, but you would have to be manufacturing these edges at nanometer level precision and deploying this thing in space and flying it around. So this gives you a sense of this kind of thing may happen. This has been studied seriously by NASA and people doing ground-based experiments to see if they can develop this technology further. But I'd say this is pretty far into the future for this game. Most work right now is concentrated on coronagraphs. Could also achieve higher starlight suppression using a technique known as knowing interferometry, which takes advantage of two telescopes separated in space, two apertures separated in space, and then using the principles of interferometry to cancel the waveform between those two telescopes. The idea is that for a given baseline of an interferometer, you can create this fringe pattern that would dramatically suppress the light, and then if you could rotate this thing, you could create this kind of image where you've completely suppressed the light and you can see faint point sources. Similar to the lambda over d diffraction limit of a single aperture, the diffraction limit of an interferometer scales as lambda over b, where b is the baseline, simply the separation between the elements of your interferometer. Okay, so starlight suppression. Let's talk about instrumental speckles. These are things that arise. They're called speckles because they sort of manifest very similarly to atmospheric, how atmospheric turbulence changes the wavefront. So these are caused by imperfections in your optical system, all the way from the top of the telescope to the detector, where you have diffraction off of and scattered light off of elements and these imperfections. This is an image showing these kinds of things. You have diffraction from the so-called telescope spiders. That is, if you've got your secondary mirror in front of the primary mirror, the arms that hold the secondary mirror are called the spiders. And so you get diffraction off of those. You have speckles caused by imperfections in the optics and things like that. A lot of things can cause this. So the spiders, the support structure for the secondary mirror. If you have any sort of obscure aperture, the secondary mirror itself. If you have segments in your primary mirror, you'll get scattering and diffraction off of those, the edges of those segments. Imperfect pointing, that is not perfect alignment with your coronagraph, for example. Imperfect coronographic masking, imperfect optical surface. All these things combine together to give you instrumental speckles that can also overwhelm the light from a faint companion. There are a number of techniques that have been developed in the recent years to try to beat speckles, both atmospheric and instrumental. Two classes of techniques. One's called angular differential imaging. This is a cartoon showing how the technique of ADI works. The principle here is you let the field rotate across the telescope, the entrance aperture of the telescope. The planet should not move relative to the star, but the speckles will. And so you use some complicated procedure to derotate the image, do a median, remove the instrument speckles that are rotating, and then unrotate the thing and stack it and see the faint point source. I love this technique because Christian Marois said he got his PhD because he decided to unplug something in the telescope. That is, to turn off the derotator for the telescope and let the field rotate. I thought that was a really clever way of describing that. Obviously, it's much more complicated than that, but I thought that was funny. So that's ADI. Another technique, chromatic speckle suppression. That is, if you take a spectrum of these direct images, then you see how the speckles change in wavelength in a fairly predictable way, whereas the planet's position relative to the star should not depend on wavelength. Its brightness may depend on wavelength, and surely does, but its position won't. And so again, sophisticated software can take these data cubes that are taken, this is an example GPI simulation, they're actually getting real data like this, and subtract out those speckles that way and reveal those fixed faint point sources. Yes? That might be a planet too. This is not my simulation, right? Imagine you're scanning over some molecular feature, right? So I don't know. If it's not moving, then it's probably a planet in this simulation. Oh, excellent, excellent. That's perfect. Thank you. That's exactly why. Yes, right. So a background star, which doesn't have such a strong change in wavelength, right? Imagine, at infrared wavelength, stars almost look like black bodies, and so they may get a little fainter as you go to longer wavelengths, right? But this thing coming in and out is not changing in position, but its intensity is changing a lot. So it's like you're going in and out of some strong molecular band, right? Yeah, cool. Okay, so let's finish up with a discussion of zodiacal light. Zodiacal light, and particularly exozodiacal light. Zodiacal light's the thermal emission caused by dust in our own solar system. Exozodiacal light is the extrasolar counterpart to that, the thermal emission from dust particles in planetary systems. It's relatively cold, peaks at infrared wavelengths. It's a pervasive background source, and the fact that you're not truly spatially resolving the disk of a planet causes this to be important because you're actually integrating over a pretty large portion of the planetary system that you're imaging. So the point is this dust is fairly optically thin, but if you integrate over a large area, it becomes important. And so this is an important background source especially for the regime of detecting Earths around other stars, because if the zodiacal brightness around extrasolar planetary systems is, say, a factor of 10 or maybe even 50 brighter than our own solar system, and we don't know, it could be, then this could overwhelm the signal that you're getting from an exo-Earth. This figure shows you the relationship between the background counts that you would get from the exozodi to the Earth as a function of exozodi relative to the solar system. And so, if it was like the solar system, we'd be down here at 1, and this relates to, what's the exposure time? So that counts as the solid line, right? So in a 2-meter telescope, even at one zodi, that is 1 times the solar system, you're getting 20 more counts from the background than you are from the exo-Earth. And the point is really the spatial resolution, the fraction-limited resolution of that telescope integrating over a large area in the exoplanetary system. As you go to larger telescopes, your resolution increases and the area you're integrating over is less. And so the ratio comes down. And so this is an important question for the exo-Earths because it really sets the size of telescope that you need. And you can see how strong this is here. The time, I can't remember, is like exposure time to reach some signal to noise probably. And so really I'm explaining just what these solid lines mean. So you can see why you would need to go, if the exozodi is high, then you need to go to larger telescopes, even if you could, in principle, detect the exo-Earth, achieve the contrast, achieve the angular resolution, you could still be overwhelmed by the exozodi if it's high. So the question of what is the exozodi is a really important one to inform the design of future imaging missions. Okay, so with all that said about direct imaging, the point is to try to take spectra of the planets. And so this is just a cartoon picture of how that's done, right? It's like take the direct imaging, put a spectrograph slit over the point of light that's the planet, disperse the light, take the spectrum. So that's all great in practice, but in principle, it's really hard. Here's just an example I pulled from the literature, Marcus Janssen, paper from some years ago, VLT observations of HR 8799c, where you see the star, of course, very strong, and then that's the spectrum of the planet. And if you didn't know where the planet was, you'd be hard-pressed to pull that spectrum out, I think. That's my own impression of this. So this gives you a sense of how hard it is to do.
What were those at?
This is spectral, spatial. Right? So the spectrum of the planet's running like this. And then spatially, you have to know where it is. And it's also spatial in this direction too. Is that right? Is this an IFU or is this? Let's just make this simple. Spectral, spatial. Right? The point is that contamination from imperfections in the optics of the instrument give you things that look very much like the spectrum of the planet. And they're even brighter. Right? And the star is obviously extremely bright. So you have to know already, in this case, where the planet was, exactly where your telescope's pointing, what the angle is, so that you get this spectrum and you know where the spectrum of the planet is. Okay, so in direct imaging, most often what we're doing is we're measuring the thermal emission of a planet. I have just a few more minutes, I think. We're looking at the thermal emission of a planet. And so the question is, what controls the planet's thermal emission? And that sort of tells you what you can deduce about the planet from these spectra. So it's really temperature, composition, and dynamics. If you're imagining planets behaving as black bodies, then you can go back to this formula that I also showed you for secondary eclipse, which relates the size of the planet to the size of the star, and the equivalent black body temperature, black body flux for a given wavelength and temperature. Just want to remind you about this parameterization of the temperature of a planet, the effective temperature, which is the integration, the bolometric luminosity of the planet integrated to equal a black body of a given temperature. This effective temperature is sort of a global property of the planet. It almost has nothing to do with the true temperature that you'd be sensing if you were looking into the planet, because it depends on what your wavelength is, whether you're seeing in and out of these molecules. Planets are not black bodies. So here are more example theoretical models, again from Jonathan, showing how strong the change is as a function of wavelength. This is a log scale. Planets with different effective temperatures. The brightness of the object, changes in the chemistry can also change as well. We need to talk about this. So I'm going to skip just a couple of slides and talk just at the very end about, so I was talking about thermal emission here, which is predominantly what's being done, which is exclusively what's being done in direct imaging right now. But I want to look forward into the future where we're going to have direct imaging at optical wavelengths, where predominantly what you're seeing is the reflected light from the planet. And so I want to just give you here and point out the signal in reflected light. This is probably going to be inaugurated by the coronagraph on the W1 mission, which would launch in the mid-2020s. And so this is not something that's of immediate relevance, but in the interest of completeness, I want to mention this. So for reflected light, the contrast of a planet, again, comes back to the geometric albedo, size of the planet, separation. This is the same thing as we were talking about for transits at secondary eclipse, except for now we have to consider the phase function. At secondary eclipse, we know the phase function is 1, but for a directly imaged planet, imagine we're here, the star's here, planet's here, the phase function depends on this angle that we're viewing the object at. And so you have to calculate what this phase function is. And so the interpretation of reflected light from a directly imaged planet has this additional complication. And I guess that's it. I'm kind of stopping suddenly, but I have another 3 hours tomorrow. So maybe that's okay. We'll pick this up tomorrow. Like I said, we'll start talking about state-of-the-art science results. And then we'll conclude also in the third lecture talking about the future. So thanks. I'm out of time. I don't know if you want more questions or... Everybody's hungry. Mike's not hungry. Right, so a flat field could, in principle, can correct for the interpixel sensitivity variations, right? But without moving it over the pixel, you don't know internally in a pixel what's happening, right? So you'd have to take a really sharp point source and put it on a pixel and then map it over it. Right, you only get one number out of a pixel, right? And so that can, in principle, remove interpixel sensitivity variations, and it does work to some extent, but then you have to ask how precise that is that you're actually making that correction. And then, is it changing in time? So inter is less of an issue than intra. Intra is the bigger issue because it doesn't calibrate out. But for example, I don't know on JWST if we're going to have like reliable flat fields. Like I've never heard anybody like say what the flat fielding strategy is for the JWST instruments. Maybe they have one, and I'm just ignorant. It's very possible, but I'm just saying that. So that supposedly is the optimal design, optimal shape to suppress the light from the star, from the physics of diffraction, which are extremely complicated. Limb darkening. Yeah. So the planet's a sphere. It's not a disk, right? So you've got the star. Sorry, thank you. Right. So. Imagine that you've actually got a sphere coming out of the board here. So you're looking at the star like this. The angle that you're coming into the atmosphere changes as you move from the center to the edge. So you're actually seeing a slant path of higher and higher degree as you go to the edge. which means you're seeing shallower into the atmosphere. The point where you reach the optical depth of 1 in the atmosphere becomes higher up. This is the star, right? So it's actually brighter here and it's fainter here, right? If you just Google limb darkening, you'll see a perfect image. Like maybe Jonathan can draw
I
it.
teach this every year. So if you imagine we're here, or this is our eyeball. This is our eye. We're looking at this is our eye looking up at the star. Okay. You see down to a column optical depth of 1. That's the surface of the star you see. So if you imagine 3 atmospheric layers in the star. So at normal, there's some column where you reach an optical depth of 1, and that's the layer you see down. This is the layer.
Go all the way
down
down,
to.
yeah.
That's the layer you see down to. At the slants, you're going through much longer path lengths, so you only see down to this layer. This is an optical depth of 1. This is also an optical depth of 1. But you see here, you're seeing deeper to higher pressure, where it's hotter. And on the limb, you're seeing deeper, you're seeing to some lower pressure level that's typically colder. The actual disk appears brighter at the center and colder as you go to the limb. If you have a temperature inversion, though, you actually see limb brightening instead of limb darkening.
So some lines in the UV, you can see actual limb brightening, but it's a pretty niche effect, I guess. So the point is not that it's mysterious, it's just very unique for each star, and it's coupled to the measurement of the transit depth. So you have to precisely correct for the limb darkening to pull out an accurate transit depth, which is the thing that ultimately tells you about the atmosphere. At the level we need to work at, it's unique to every star. Yes? I mean, the normally thing that what you do is you characterize the star and then you go to some pre-computed table of atmosphere models that tell you the limb darkening. But what I'm also saying is, okay, that maybe works to first order, but the illustration that I showed, which is saying if you get the limb darkening wrong, say because you got the temperature of the star wrong by 100 Kelvin, which is very possible, then you could have fake atmospheric signals for the planet. So that's for GJ1214. For example, if we'd have gotten the temperature of the star wrong by 200 Kelvin, fixed the limb darkening, we would have had a water vapor feature in the spectrum of the planet consistent with a high mean molecular weight atmosphere, just because of the limb darkening. Yeah. I think it's just empirical. Yeah. Yeah. Naturally. Mike? Yeah, so that's the subtlety of when you fit for it. That's why a lot of times the most that we could pull out from the data is a single coefficient. And that's bounded, but yeah. So there have been applications of 3D hydro models of specific planet host stars, 209, HD 209, 458, and HD 19733, and those seem to reproduce the data much better than your standard 1D static models. But then they're also become difficult to compute And so it's not really feasible to do it for every star. You're looking at every planet around. And then you still, personally, I would still worry that you're not getting it quite right. And so my strategy would always be try to get as much data as you need to actually break the degeneracy in the data between the limb darkening and the transit depth. And so you make a purely empirical measurement. Now cross-check what you get from the empirical with the models, right, for a sanity check, which is what we were doing for 1214b, right? But yeah, so that's my personal approach.
When you're trying to measure, I just want to understand this, when you're trying to measure the spectrum of the planet moving in front of the star, the idea is that you're looking at a particular wavelength.
The limb darkening is wavelength dependent.
Exactly. So
Yeah.
if you're looking at some wavelength, it might get brighter or less bright just because of limb darkening and not because.
That's right. The example for GJ1214 is that we were looking for water in the planet's atmosphere, but the star is so cool that it has water in its atmosphere too. And so inside that water feature, the limb darkening is totally different because you're instead of this versus this, it's now like this versus this or this versus this. You like completely change the level, the atmospheric layer that you're seeing in because of the opacity in the atmosphere. For an F star, it probably doesn't matter. There's some like, it's like some like if you looked in the infrared, the way a limb darkening coefficient would change would be like fairly linear. Right, but
What's the algorithm that you use to get this?
well, in the transit light curve itself, you have coefficients for some limb darkening law that describe how the transit bottom really should curve, and so you have a parameterization for that. So you can either put in parameters that you get from some stellar atmosphere model, or you can just solve for them at the same time you're solving for the transit depth and the other transit parameters. Mm-hmm. Right, that's the thing that you're trying to pull out of it. Although we don't correct for the limb darkening, right? It's more of you solve for these things all simultaneously. So you count for correlations between parameters and degeneracies between parameters. But yeah, that's the thing that you're ultimately deriving is what is the transit depth for just a black disk over a bright disk. Okay?
All right, thanks a lot.
Cool.